shooter games, actions like firing while moving or reloading mid-jump are extremely common. For our game, we've chosen a high-mobility, hero-based shooter format. That means players have a wide range of tactical options, freedom of movement, things like sprinting, sliding, crouching, climbing, and more. With this level of complexity, we needed to build an action system that's not only solid, but also highly expandable so it can support all these dynamic and fluid gameplay possibilities.
Our animation blending framework is built on the layered dynamic blending strategy from Unreal Engine's advanced locomotion system. By independently adjusting the blending timing on layering strategy of body parts like the head, spine, and arms, we were able to achieve a wide range of flexible animation combinations
tailored to different movement types and intensity levels. For example, when a character reloads while sprinting, the legs handle the running motion while the hands perform reload animation. Each body part has its own job, and all parts must coordinate seamlessly. To make this happen, we broke down natural human motion, figuring out which details are necessary for immersion, which ones are not. Layered blending means exactly what I mentioned earlier. When a character is playing a base animation, we can stack additional animations on top of it, depending on the character's current state, standing, crouching, sliding, or otherwise we blend the right actions accordingly.
On top of that, our team further upgraded the blending system, enabling it to dynamically coordinate animations based on custom rules. We refined left and right hand coordination to ensure smooth transition between shooting and skill use. With this, the framework successfully preserves a high degree of control freedom, ensuring that even under complex inputs and movement states, character animations remain stable and free of major distortions. But first, let's go back to a more fundamental question: the transition from standing still to moving. It's a basic yet often overlooked process, and one that revealed key flaws in our original system. The default movement component in Unreal Engine uses a single acceleration model, which results in a purely linear motion curve.
Take the most basic example starting from a standstill. UI's default behavior is simply linear acceleration, just like the basic physics formulas we learned in middle or high school. To achieve a more responsive feel, the default acceleration value is often set very high, say 4,000 or even 8,000. The result: characters instantly burst into motion from a standstill, almost immediately hitting top speed. But this approach leads to an unintended consequence as the character operator. I personally found it perfectly acceptable. My character could run with agile responsiveness. However, enemies on allies observed that the movement trajectory lacked physical realism. Specifically, there was no visible acceleration phase. The character instantly launched from a stationary position.
To resolve this issue, the team studied industry standard solutions. Through rigorous testing, we developed a dynamic acceleration system. We defined acceleration as a piecewise function of current speed based on the player's real-time velocity range. Distinct acceleration values are applied accordingly. This ensures players retain agile initial responsiveness during operation while maintaining physically plausible movement for observers. Beyond ground movement controls, the team prioritized aerial maneuverability.
We refined the air control system by implementing dynamic adjustment logic. Using pre-jump velocity data, we dynamically tune mid-air acceleration, maximum horizontal speed.
This controlled variable acceleration concept was also applied to sliding mechanics. Sliding is the most frequently used movement technique. Given the game's complex and varied terrain, achieving physically authentic slide physics became challenging. For instance, we wanted uphill slides to feel laborious, while downhill slides should feel exhilarating.
Our initial approach leveraged real-world physics principles. We implemented slope-angle-dependent acceleration curves, which interact with frictional deceleration to accurately replicate slope-based slide dynamics.
Nevertheless, the diverse terrain and elevation changes posed significant challenges to movement fluidity. When utilizing advanced climbing mechanics to traverse multi-level environments, preserving motion fluidity and speed continuity proved particularly difficult. Using limited fixed animations for all climbing scenarios resulted in jarring transitions, sprinting toward walls, followed by sluggish climbing animations. This have the perceived fluidity and momentum. To maintain seamless motion continuity, we categorized climbing into distinct parameters: obstacle height, player velocity, surrounding space, etc. The system evaluates these conditions selects appropriate configurations based on results, and triggers corresponding animation.
We continuously predict players' instinctive reactions of intended actions. By scripting potential scenarios and anticipating player responses, we design responsive mechanics that align with natural behavior. These undergo iterative testing cycles until achieving mechanics that closely match player expectations. Approaching the wall slowly initiates a deliberate climbing animation. If sufficient space exists beyond the obstacle, post-climb dash preserves forward momentum.
A highly extensible animation blending framework, dynamically adjustable speed controls, and granular scenario detection collectively form the core architecture. After ensuring technical precision in movements, we infused actions with character personality.
We crafted an immersive Farlight 80 for universe, where every character has unique lore and backstories. Distinct personalities and professions demanded bespoke movement styles. Each character received customized animations. Queta's idle pose exudes defiant confidence, head tilted casually, hands tucked in pocket. Identical actions manifest uniquely across different characters. Duck's Widey's animations were particularly memorable. Cartnish-Light exaggerated motions with frantic energy, though often immersed in tense combats and areas. Ducky consistently injects humor and levity into battles.
While visual design sets the foundation, true lifelike authenticity required motion capture technology. We recorded nuanced performances by real actors which were mapped onto characters.
The creative synergy between actors and directors oft unyielded improvised brilliance beyond script's moments of organic inspiration.
To maximize mocap efficiency, we predefined every character's performance direction. Take Bo, we analyzed Jack Nicholson's iconic Joker performance.
His theatrically exaggerated style perfectly suited this deranged villain. When crafting his movements, we paid homage to charismatic antagonist mannerisms often infused with calculated madness. The resulting animations achieved exceptional impact.
Seamlessly integrating these performances with movement systems made Farlight 84's characters truly come alive. This summer, our meticulously polished update is going to be launched. We invite all FPS enthusiasts to experience and witness Farlight 84's continued evolution. Your feedback remains vital to our iterative refinement.